All right, good morning. We'll take a look. I hope you guys are doing well. Thanks for coming to class. So I will cancel Wednesday's lecture. We'll have today and then no class Wednesday. I'll also cancel my other class. And so I don't know if you have other classes on Wednesday, but if you decide you want to leave a little bit earlier for Thanksgiving break, then I guess you have my blessing. I have already posted up homework 5. That's up, and I think we'll make homework 5 the last homework for this class. There's like a little bit more with the Gibbs sampler that we could be doing. Homework 5 does touch upon the Gibbs sampler, but it's up now and it'll be due at the end of week 10. And so hopefully that should be enough time to kind of cover everything. And yeah, we'll go from there. Okay. So let's take a look. So last week we introduced the Gibbs sampler as a Markov chain method. And we said, for the Gibbs sampler, you're going to produce a random sample. Okay, it's again our distribution exists in a high dimensional setting, and rather than trying to propose all the coordinates of this high dimensional thing, so let's say you have a distribution in 3 dimensions, rather than trying to propose all 3 coordinates at the same time, we're going to propose one at a time. And to propose that one coordinate, you just plug in kind of constants for the other two coordinates. And so once you plug in constants for the other 2, basically your distribution boils down to a univariate distribution, and you just generate something from that univariate distribution. You can use a rejection sampling method. You could use inverse CDF method. You can use Metropolis-Hastings algorithm, but basically you go through and you generate a new value for that one coordinate, and then once you get that, then the next coordinate is unknown, and you hold the other coordinates constant, and you kind of go through that. So it's if you recall from 102A, the coordinate descent algorithm, where you kind of hold one thing and you optimize, it's similar to that, except rather than optimizing and finding a minimum, you hold the other values constant. It becomes a distribution of one variable rather than a function of one variable. It becomes a distribution of one variable, and then you randomly sample from that distribution of one variable. And our general theme has been basically it's easier to work in one variable or one dimension than it is to work in a higher dimension. So a lot of times we try to take high dimensional problems and reduce them down to lower dimensional problems. And so so this is just this slide is a quick review of the Gibbs sampler. So again, so you might have some variable x in some unknown dimension d, and you have, this is your kind of current value, x at time t, and then to produce a random sample at x at time t plus 1, you just kind of create conditional distributions where you hold everything else constant, and you sample, one coordinate of the variable at a time, right? And depending on your situation, figuring out what is the distribution of this one variable if you hold everything else constant may or may not be a straightforward answer. So, in some cases, like if you have a bivariate normal, you hold one thing constant, it's normal in the other direction. So that's simple enough. But if you have something, something more complex, holding the other variables constant, we'll simplify it down to a univariate distribution, but figuring out the PDF of that univariate distribution may not be straightforward. Okay, so in a situation where the Gibbs sampler works very well is what we call a hierarchical model, okay? And the reason why the Gibbs sampler works well for hierarchical models is that they are already set up in these kind of conditional distribution setup. So then, so trying to figure out the conditional distribution, you know, once you kind of hold everything else constant, this part where you turn it into a conditional distribution, a univariate conditional distribution, this part which is hard over here isn't hard because it's the distribution is set up in this form already. So, so for this, let me see if I can turn off these. For our example, we will revisit, if you remember the baseball example, the beta binomial baseball example. I think I introduced like the first week of class, okay? And so remember in this example, we're doing, taking a Bayesian approach. So there is a parameter, theta, which we call a player's baseball batting average. And, we're going to treat batting average as, some number between 0 and 1, representing the probability that someone gets a hit when they have an at-bat. And we said we're going to treat this variable theta as an unknown random variable. Okay, so rather than just a single unknown value that we would, which is how we would approach it in a frequentist world, we're going to treat this as a random variable. And for our baseball example, we used a prior distribution. Prior distribution with shape parameters 81 and 219, and that produced this kind of this distribution where the peak was around 0.27-ish, or the mean is around 0.27, and most of the values are between 0.2, above 0.2 and below 0.35, and that kind of reflects just our understanding of batting averages in baseball, that to be a pro baseball player, your batting average is generally over 0.2, otherwise you're going to get kind of cut from the team, or you'll get sent down to the minors or something. And again, just in the history of baseball, the greatest batting average of all time is 0.36, something around there, 0.362. And so, getting anything higher than 0.35 is, we can kind of put a very low probability there. All right, but admittedly, the choice of using these parameters 81 and 219 is arbitrary, but we just chose them because it produced, the distribution that we liked. So I'm taking this example from the textbook Doing Bayesian Data Analysis. This is the one with the dogs on the cover. What we're going to do is we're going to create a hierarchical model. All right, and in the hierarchical model, when we create our prior distribution, we are not going to use the numbers 81 and 219. Okay, so remember, for our baseball example, we said, we have this distribution that goes from, say, 0 to 1, and if you choose the shape parameters 81, 219, you're going to get a peak, or a mean at least, of around 0.27, and this is, beta. These are your two shape parameters. This is the prior distribution for theta. Okay, but you might say, well, how did you pick those numbers, 81 and 219? And arguably, yeah, it was an arbitrary choice. So in a hierarchical model, we are going to treat these numbers, 81 and 219, these will be random variables themselves. So rather than saying we're going to pick 81 and we're going to pick 219, and these are based on my thoughts and opinions on baseball, we're going to treat those numbers, 81 and 219, as random variables themselves. And so maybe the true number is not 81, but maybe the true number should be 80 or 85 or 77 or something around 81. Maybe the true number shouldn't be 219, but should be something else, something around there. And maybe not even 81, 219. Maybe like we scale it down to like 40 and 110, or maybe we scale it up the other way or something like that, right? So there's different things that we can choose for these values. And so what that means is we have a distribution, a random variable distribution for the shape parameter alpha. And we also have, beta itself is a random variable also with its own distribution. And so these parameters, alpha and beta, okay, because they're parameters of the prior distribution. So remember, in the beta binomial model, we're saying the outcomes in the data are things like zeros and ones, right? These are either, outs, hit. All right, these values of zeros and ones, these come from basically a Bernoulli. Are there two L's in Bernoulli? I don't know. In a Bernoulli distribution, right? Basically, we're flipping a coin every time the baseball player goes up to bat. That's a Bernoulli distribution. The Bernoulli distribution has some parameter theta, okay? The Bernoulli distribution has some parameter theta. We're trying to figure out what the theta is based on our data. We said we're taking a Bayesian approach. Theta comes from a prior distribution. And now we're saying, all right, what is that prior distribution? When we first introduced the class to it, we said we're going to use the shape parameters 81 and 219. But now we're going to say, I don't like how arbitrary these numbers 81 and 219 feel. I want to treat those as random variables themselves, okay? So we're basically turning away from our own arbitrary choices, and we're just trying to kind of figure out all of these things, okay? And so these things, so this is our parameter that we're trying to figure out. And these parameters of the prior distribution, these are known as hyperparameters, right? So to kind of indicate that they are parameters of the prior distribution, we give them a special name, hyperparameters, okay? All right, so the distribution for alpha and the distribution for beta, those, again, we're treating those as random variables, and we're taking a Bayesian approach for that. So those things have their own kind of prior distribution as well. And the prior distribution for the hyperparameters are known as hyperpriors, okay? So there's just like all of this, hyper that, okay? So unknown theta is your parameter. The prior distribution, you have a prior distribution for the unknown theta, your unknown parameter. That prior distribution might have its own parameters, which we call hyperparameters. And those hyperparameters have their own prior distributions, which we call hyperprior distributions. Okay. Is that okay? Now, those hyperprior distributions themselves, again, it's kind of like turtles all the way down. So those hyperprior distributions themselves may also have their own parameters, okay? And if we treat those as things, we would call those hyper parameters. I'm totally serious. Hyper parameters, and those themselves may have their own distributions. They're hyper prior distributions, and you can keep going off to infinity. Okay. However, just usually after like one layer of hyperpriors and hyperparameters, we usually kind of stop. We usually go to some kind of uninformative hyperprior, okay, which would just kind of be like either a uniform distribution on 0 to 1 or something like that. Okay, but yes, it is technically possible for this thing. It has its own kind of distribution that generates it, and that distribution could have its own parameters, and you just kind of have it keep adding hypers, and you have the hyper priors, the hyper priors, and so on and so forth. Again, it just gets it's kind of like one layer on top of another layer. Like, have you guys seen the movie Inception? I don't know. All right, it's like over a decade old now. It's a fun like heist movie, but they go inside someone's dream, and then once they're in that dream, they go into another person's dream, and it just kind of keeps going layers and layers down. And it's kind of like this, but with hyper prior distributions. Okay, so what kind of hyper prior distribution should we put on alpha and beta? All right, so in the baseball example, we had chosen 81 and 219 as these kind of arbitrary values for our prior distribution. And knowing the beta distribution, those values 81 and 219, these were kind of like, we might call them pseudo counts, in that effectively we could have pretended that we saw this player have 81 hits and 219 kind of misses in this fictional scenario where they had 300 at bats. Okay, so again, the way we kind of update the beta distribution is as you gather more data of more hits and more outs, you basically take the number of hits and you end up adding them to your alpha. You take the number of outs and you add them to your beta, and that kind of gives you your posterior distribution. I don't know if we remember all of this from our kind of our first homeworks and stuff. And so when we set up our prior distribution and we had these numbers 81 and 219, we hadn't actually, these aren't actual data values, but we just kind of use them as like these imaginary counts of hits and outs for our typical baseball player, and then we update them accordingly as we see values. Okay. So these values 81 and 219 produce a beta distribution where the mean is 27%, which is 81 divided by 300, and then but the mode, the peak, is actually at we can find it at omega, which is you subtract 1 from the numerator and 2 from the denominator, and the peak ends up being at 0.2685, 80 over 298, okay? And that seems kind of reasonable for a batting average, all right? And what we can do is we can say we're going to use these numbers omega and k as a way to kind of backward solve for what alpha and beta are. So it's kind of like you pick where your peak wants to be, and then you and so if we say, I want my peak to be around 27%, 0.2685 or something like that, okay, we can say, all right, I want a beta distribution where the peak is around 0.2685, and kind of how confident do you want to say, like how much data are you going to be basing this off of, like a pseudo count? You want to say, I'm basing this off of, say, 300 values, I'm basing this off of 100 values, I'm basing this off of 1,000 values. So kind of, with 81 and 219, I could, if I do 81 divided by, I would get 0.27, right? So this is 81 divided by 300. I could also get, the same mean by doing 27 divided by 100, right? And that would basically become 27 over 27 and 73, okay? And so I would have a similar shape, right? So if I do A is 27, B is 73. Let's do sequence from 0 to 1. Okay, so this is one possible distribution, and I could do the same thing, except we're going to just replace A. Maybe I'll call this A1. It's going to be A times 3. And if I just kind of scale everything up, I would get a similar distribution, but that just end up being narrower, right? And so this kind of reflects like how confident do I want to how narrow do I want my distribution centered around 0.27, right? So this is if I use shape parameters where A1 is 27 times 5, so what is that? 135, okay? Here I'm using 81, here I'm using 27, or I could even scale it down even lower. And this is for the prior distribution. I could kind of, have something wider, right? All of these distributions are centered at 0.27, but they're of different widths, kind of depending on how wide we're doing it, right? And so we're basically taking that idea, except I'm choosing the peak using omega, and I'm going to use this factor k. So rather than 300, we could scale it up to 500 or 200 or 100 or something like that, right? So here we're going to choose k as some arbitrarily selected constant of 300, and we will treat omega as a random value drawn from a hyperprior distribution. And so this selection of omega will then determine the values of alpha and beta. All right, so if instead of changing how wide we want, let's say we want to keep it at 300, so I have 81 and 219. This is the other way I could alter this. Let me just sweep all of this away. Okay, so we could have a distribution center that looks like this, but I could kind of just pick some other numbers, right? I could pick, say, 70 and 230, and that would kind of slide things down that way. I could pick, say, 100 and 200, and that would slide things up a little bit higher, okay? Here, I'm going to do omega, or maybe I'll just call this W, 0.2685, and K is going to be 300. And we're going to kind of backwards solve using A is going to be W times K minus 2. Oops. So if I do that, A should be, I'm sorry, K minus 2 plus 1. Okay, and then B is going to be 1 minus omega times K minus 2 plus 1. All right, so these should give me values of, 81 and 219 basically. And so if I do this, this is the distribution I get, and I can kind of change this number from 0.2685 to say 0.2985, and that will just kind of slide things up. I can change it to say 0.35, and that will center everything to be at 0.35, So I can kind of fiddle around with this, and this will determine like what my new alpha and what my new beta values should be, right? So if I change omega to be 0.2, my alpha and my beta values are going to be 60.6 and 239.4, which is going to create a distribution centered at 0.2. So that's basically kind of what we have here, right? So we're going to kind of we're going to treat omega, this W value, omega, as a random value drawn from a hyperprior distribution, and that value is going to kind of determine the values of alpha and beta, right? So, so what kind of hyperprior distribution should we set for alpha and beta? Okay, so again, alpha and beta should just be these number values like 81, 219, 100, 200, or some kind of value, some kind of set of values. Omega is some number between 0 and 1, itself, maybe having a peak around 0.25 or something. Okay, so omega itself comes from a beta distribution, and this beta distribution is the hyperprior distribution of omega, and we use that to generate values of alpha and beta. And so in turn, we need to select some values for the shape parameters of this beta distribution for omega. And once we have that distribution for omega, we will generate the values alpha and beta there. Okay? All right, so this is kind of our hierarchical model that we have. Oh, here, let me give you, before I forget, let me give you our view quiz answer for today. Okay, our first letter is A. A as an apple. A as an apple. All right, so K is going to be just some arbitrary number. Here we're going to just use 300. And then omega is some random distribution. And omega comes from omega is a random value coming from the hyperprior distribution. That hyperprior distribution is beta, which has its own hyper parameters. But here we're going to just arbitrarily select these numbers, right? So at some point we have to kind of arbitrarily select some numbers. But now that we have omega and K, we are going to use that. So omega is randomly generated. We're going to use that to pick what our alpha and beta values should be. Once we have our alpha and beta values, that's going to determine our theta value. And once we have theta, that's going to go into the Bernoulli distribution, which will be used to generate our zeros and ones, which is our actual data values. So we're kind of trying to come up with some kind of system that says this is where our data values are coming from. All right. So this is what our distribution looks like, okay? Our diagram looks like. So the actual values are Bernoulli, zeros and ones. These are determined by some unknown parameter theta. Theta itself comes from a beta distribution with shape parameters alpha and beta. Alpha is omega times k minus 2 plus 1, and beta is 1 minus omega times k minus 2 plus 1. So we're using the same omega value. That omega value comes from its own hyperprior distribution, which is a beta distribution with these shape parameters here. Okay, so once we have this set up, we can use this hierarchical model to explain the data, the hits and the outs of multiple players. So when we first started, we just said, here's one player who has an unknown batting average theta. But we might have a team of baseball players or a team of batters, and we want to have some kind of distribution set for all of these players. And so player 1 has his own batting average, theta 1. Player 2 has their own batting average, theta 2. Player S has their own batting average, theta sub S. Okay? And so in this case, we have the same kind of hierarchical model. All right, we have some arbitrary beta distribution that generates an omega, and that omega is going to generate our prior distribution, and each individual gets a theta s, their own kind of, each player gets their own theta value drawn from this beta distribution, and that individual player's theta value is used to generate the hits and outs when they actually bat. Okay, so here I'm putting little subscripts on this thing. So so this thing looks almost exactly the same, right? But we're going to say now we have different values, theta sub s, one for each player. And once we have these different values for each player, we can use that to explain this one player's hits and outs and another player's hits and outs, right? So you can, on your baseball team, you might have a good batter and an okay batter and maybe a poor batter. And they're going to have different values of theta, right? The good batter might have a theta sub s of 0.3, and then the mediocre player might have a theta sub s of 0.25, and then the not so good player might have a theta sub s of 0.2, right? And that would kind of be, the range of kind of your excellent players to just your okay and not so great players on your team. And depending on that, that's going to be determine whether you get hits or outs. Okay, of course, the hits or outs themselves are just random draws. So even if you have the good player or just the average or the poor player, because based on just kind of random coincidence, you might get a streak of hits or streak of outs for either of these players. So this is, I guess, to kind of illustrate how there's multiple things. This is one way for us to illustrate this. So we have this hyperprior distribution. This is technically a beta distribution. This is going to generate an omega value. That omega value is used to determine what our alpha and beta parameters are, and that goes into our beta prior distribution. That beta prior distribution generates a theta value. So here we have theta 1, which is player 1's batting average. And that goes into a Bernoulli, which generates some zeros and ones for the hits and outs. That same beta distribution is used to generate a theta for player 2, which is used to generate ones and zeros. And we have player 3 and player 4 and a whole bunch of players and something like that, right? So this, I don't know if this does any of a better job of illustrating the fact that you have multiple different theta values coming, one for each player, coming from the same beta distribution. beta prior distribution, and each of those things determine the hits and outs. That beta prior distribution has its own shape parameters, alpha and beta, which are coming from a hyper prior distribution. This is this diagram on the left can be shown using a plate representation. Okay, so rather than having to show each of these things, the plate representation kind of just shows the different parameters going into play here. And so here we are saying the actual values, yi, come from a Bernoulli distribution that is determined by this parameter theta sub s. Okay, and this theta sub s is understood to be a random variable. Okay, and then we have a plate with a little subscript s here to indicate that this relationship exists for each of our different players. All right, so again, this kind of theta generating y's, okay, is shown, over here for player 1, player 2, player 3, player 4. Okay, and then we're going to say each plate, meaning the kind of the theta s going into each plate, comes from the beta distribution alpha and beta. All right, and that's shown here. So this is a plate representation. So sometimes you might pick up a textbook, or you might pick up a journal article where they illustrate kind of the Bayesian relationships between all of these things, and they might use a plate representation to show that. Okay, so what does this look like? So let's say we have this big matrix of data with all the kind of hits and outs of maybe 10 different players. And so y sub si is the ith kind of at bat, represents the outcome of the ith at bat for player s. So, player s goes up to bat multiple times during the game, and sometimes that player gets a hit, sometimes that player gets an out, and we're going to record that the outcome is either 0 or 1. And so we want to get the estimates of all of the unknown parameters here, right? So what are the unknown parameters that we have to estimate? Okay, well, there's technically 11. We have 10 different theta values. We need to figure out the theta for each of our S players. We have 10 players, so we need to figure out the batting average for player 1 and player 2 and player 3. I probably should have picked 9 or something, because that's how many you have in a batting lineup. But I guess if you have a substitution, maybe you have 10. So we'll have this, okay? Theta sub s, we got 1 for each player. And then, but those theta sub s's have come from a beta prior distribution, and that beta prior distribution has shape parameters alpha and beta. And the way we're determining alpha and beta is using this unknown parameter omega. Okay, so we have to estimate what omega is, okay, which determine what alpha and beta are. And then we have these other arbitrary parameters, k and a omega and b omega. And these were arbitrarily selected, and those we aren't going to infer from the data. So, again, we could have placed hyper priors on these things, but at some point you've got to make some arbitrary choices. And right now we're just kind of, removing ourselves, I guess, one generation or one level away, so that our direct influence over the choices are felt a little bit less, and we let the data influence it a little bit more. Okay, this looks a little bit scary, but it's just the joint prior distribution, total joint posterior distribution given all of our data, right? So we are trying to figure out what is the distribution for theta 1, theta 2, our 10 different player thetas, and omega, given the big matrix Y of our data, and these hyper parameters that we have selected. Okay, so we've selected this A and B and K, and what we want to do is we're going to use Bayes' rule, and we're going to say, okay, well, this is going to be the likelihood of our data Y given the unknown parameters theta 1 through theta 10 and omega times the prior distribution of theta 1 through theta 10 and omega given just our so these are the kind of arbitrary hyper parameters that we've selected, and so we don't have any explanation for these. Again, some arbitrary choice that we have to make at some point, divided by the marginal probability of just our data matrix Y. And kind of keeping that, to simplify that, we're going to just say, well, it's proportional to this. Okay, just get rid of the denominator, and because this is going to be a constant, so we're going to just say the posterior distribution is proportional to this, and the product of our Y given our thetas and omega and the prior of thetas and omega, we can just treat this as the joint distribution of basically everything. I don't know what's going on here. Joint distribution of everything given our arbitrary choices. All right. So again, we do have to make some arbitrary choices, but now this omega is not arbitrarily chosen. Now, because of the hierarchical model, and the promise I made to you at the beginning was that, factoring the joint distribution of everything is difficult, sometimes difficult, but it's easier for hierarchical models. And so this is where the hierarchical model part comes in. We're going to say, well, you know what, we can break up our big data matrix Y, and we can just say, hey, let's look at player one. Player one has some set of values of hits and outs, okay? And player one's hits really only are determined by the theta 1 of player 1, okay? We don't, player 1's hits and outs aren't determined by, player 2 or player 3 or player 4's hits and outs, okay? And so we're going to factor this joint distribution of everything, our total Y data, into just kind of its own little components here. So we're going to say, what is Y1 given theta 1 times the probability of Y2 given theta 2, and we can do that for all of our players up to Y10 given theta 10. All right, but then we all of these, okay, each theta 1 value is comes from the beta distribution. So theta 1 depends on what omega is and what k is, and theta 2 depends on what omega is and what k is, and all 10 of these theta values are determined by that. And then omega itself comes from a prior distribution, its own distribution with shape parameters A and B, A omega and B omega. Is that okay? Each line here. All right, and here I'm just kind of rearranging these terms here. And so we're going to have Y1 given theta 1, and theta 1 determining depending on omega and k. And we can switch from omega and k to alpha and beta because that's just a direct relationship. You two do, omega times k minus 2 plus 1, and 1 minus omega times k minus 2 plus 1 to determine our beta. And so I'm just rearranging the terms here. But basically, we're taking the joint matrix of all of our data and splitting that up into basically each row for each individual player. And we're only trying to explain each row of data given each player's theta values. All right, so this is the this is the row, and let's kind of try to explain this. So I'm saying we factored the joint distribution of everything into distributions of each row. All right, so into basically distribute. So each row in Y is the result of random draws from a Bernoulli distribution that depends only on that particular player's batting average. Each player's batting average is the result of a random draw from a beta distribution that depends on the shape parameters alpha and beta, which determine the kind of prior distribution, and those shape parameters alpha and beta are determined by omega and k, and the omega itself is a random draw from a beta distribution, which depend on the values A, omega, B, omega, and K, and those were arbitrarily selected by us, all right? So, so now we want to generate random draws from this joint distribution of everything. We're going to use a Gibbs sampler. So we want to create like, what are some random, we want to create like, what's the distribution of theta 1, what's the distribution of theta 2, what's the distribution of theta 3, because these, ultimately we want to get the posterior distribution for all of these things, and we're going to create or estimate the posterior distribution by generating random samples of what possible values of theta 1 are, what are possible values of theta 2, and so on and so forth, and we're going to use a Gibbs sampler to do that. Okay, let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat is our second view quiz answer. Okay, so we want to sample from this posterior distribution. We want to ultimately get a sample of values that could represent what theta 1 are, and sample values for what theta 2 are, and so on and so forth. Okay. The posterior distribution that we want is a distribution over 11 variables, which are the 10 theta values and the omega value, which determine the which will ultimately determine the shape of the prior distribution for theta. And again, because of the hierarchical nature, when we want to sample a value for theta for player S, the only values that are relevant are the ones that are involved for theta sub S. So when we're trying to figure out, okay, what is the posterior distribution for theta 1, we could eliminate everything other than basically everything for theta 2 through theta 10. Okay, we really only need to figure out, okay, what's the posterior distribution for theta, or I guess posterior distribution of theta 1 is just going to be related or proportional to the likelihood of the data for y1, that one row given theta 1, times the prior distribution for theta 1 given the shape parameters A and B. So you have this joint distribution for all of these players, and they are truly all kind of related through, going back through this, theta 1, theta 2, theta 3, and theta 4 aren't coming completely out of the wild, right? They all are related to this beta prior distribution, which is kind of like this, I guess, this ancestor for each of these things, okay? But once you have each individual players, that's going to determine kind of the Y1s, you know, the zeros and ones and their actual hits and outputs, right? So there is, you know, it's like siblings or something, cousins in some kind of family relationship. You know, they're not completely unrelated. They are related to each other through kind of their, I guess, ancestral prior distributions, okay? However, you know, when we're trying to figure out our posterior, we really only have to care about that individual player's data and the kind of the immediate prior distribution here, okay? But these values, alpha and beta, are all kind of interlinked with it, you know, taking into account all of our data here. So, so I said, I wrote, we're familiar with the relationship between the posterior distribution of a Bernoulli or a binomial data with a beta distribution prior, and we said, you know, you have kind of the individual hits or outs, the zeros and ones, which are drawn from a Bernoulli distribution. Okay. And then you have the kind of the number of trials for that particular player, and then you have the and so if we take that into account, the posterior distribution, you'd use your prior value alpha plus basically the sum of your hits, okay, and then your prior value for beta plus basically the sum of your outs or your zeros. So how many successes and then how many misses do you have is going to be your n minus the sum of the y's, okay? And k is kind of the total number of hits, all right, for player S. So if we say k is the total number of hits, then we can say, you know, your posterior distribution for theta is alpha plus k, and then with shape parameter beta minus n, or plus n minus k, right? So that's all we're going to say here. Okay, so turning this into code, this is kind of what we can write, okay? So J will be like how many iterations we want to do, and like, again, we're just trying to, so we have a posterior distribution, and we can just leave it at this, but let's say we want to generate random values, okay? We can do this in this kind of fashion here. So we can say, here, I want, you know, 10,000 values for our posterior distribution. So we've got alpha determined by omega times k minus 2 plus 1, beta being 1 minus omega times k minus 2 plus 1, okay? And then the Gibbs sampler here is just going to be like, okay, just generate a random theta value for a particular player. And so we're going to have, for each player, S, so I'm going to have S columns. So I'm going to have 10 columns, but I'm going to have, like, for column 1, player 1, I'm going to have like 10,000 values, random values from their posterior distribution. And so for that, I'm just going to just draw a random beta value using our posterior solution, alpha plus k and beta plus n minus k for player S. And we're going to do this 10,000 times. So we're going to get 10,000 values for player 1, 10,000 values for player 2, and we're going to get random distributions for each of these things, okay? But we have one more parameter to estimate for, and that's the omega, right? So omega is used to determine what our alpha and beta are, and that itself is not as straightforward, right? So what is the conditional posterior distribution for omega? That's not as straightforward. We don't quite have this relationship set up. So what can we do? Well, we can use the Metropolis algorithm. So we're kind of using, you know, the different tools we have in our arsenal here to try to figure this out. So for the Metropolis algorithm, right, what is the posterior distribution? Well, figuring out the posterior distribution a little bit tricky, but all we need is a function that is proportional to the posterior distribution. And you know, the textbook also shows the process to kind of walk through to derive this analytically. But you know, if you're kind of stuck and you're like, well, I don't know how to derive this analytically, can we just approach this? We can, right? So from Bayes' rule, we know the posterior distribution is just going to be proportional to the likelihood times the prior, and that's going to help us out, right? So this is we only need to figure out something proportional, which is nice. Okay, so the hyperprior distribution for omega is a beta distribution. with some arbitrary values, A and B. And so for A and B, I'm arbitrarily choosing 3 and 7. And what that's going to do is it's going to be a beta distribution. And again, the beta distribution is always between 0 and 1. But with shape parameters 3 and 7, you have this very kind of wide distribution. Whereas once you have 81, 219, you know, it's kind of a lot more narrowly focused around the thing. So the omega can come, you know, anywhere kind of close to 0.3, a little higher, a little bit lower. And once you determine that, then it's going to determine what alpha and beta are, which will be a little bit more of a tighter range there. So I'm arbitrarily choosing 3 and 7 here. And in our hierarchical model, omega determines the values of A and B. And we chose using kind of this relationship between omega and K arbitrarily being chosen to be 300. Our posterior distribution is going to be proportional to the likelihood of all of our data times the prior on all of this. And we just need something kind of proportional to it. So what we're going to do is we're going to take all of the sampled values for theta s, okay, and our current or the proposed value of omega, because again, for the Metropolis algorithm, we just need to compare the current value of omega and the proposed value of omega to make a comparison. And so we're going to calculate, okay, what is the likelihood of our data? So we're going to say, all right, d binom of basically how many successes did I get? So we'll have our the sum of the y's. So that's going to give us, like, we had 5 hits in 15 at-bats or something like that, right? So k is going to be how many hits you have, n is going to be how many at-bats you had, and we want to know, okay, what is the likelihood of our data, and we'll use that using d binom. And we're going to do this for each player, right? And then we're going to have to calculate the likelihood of theta given alpha and beta, right? Alpha and beta are determined by omega and k. And so we're going to say, okay, what is the likelihood, d beta, the density function, our PDF, for this particular value of theta, the value that, that we've sampled, given our alpha and beta. And then we ask, okay, what is the prior for omega, this proposed value of omega? So, or our current value of omega. We're going to say, okay, what is the PDF for this particular value of omega given, you know, the arbitrarily chosen values of 3 and 7. And because we're going to be dealing with some really small probabilities, we're going to use log probabilities instead. Because when you have really small ones, you can run into underflow errors just because of floating point math here. All right. Is this okay as far as getting our posterior distribution? So we just have a whole bunch of these likelihoods. The likelihood of our data, we've got 10 of these, okay? And the likelihood of their, in this case, theta s is also part of our data, okay? And then the prior is the prior distribution on omega. And we're trying to determine, you know, what is the posterior distribution of omega given our, basically all of our data here, okay? And here we're using the sampled values of theta to determine this. So this is what it kind of looks like. I've got basically the log probability function for a proposed or current value of omega with a vector of theta values, okay? So we have, we're going to have 10 theta values that are kind of current proposal here, okay? So we're going to figure out, using omega and k, we'll figure out the corresponding what alpha and beta are. All right, so maybe 81, maybe 219, maybe something else, maybe 40, maybe 100 and 200, or maybe 70 and 230 or something like that for what alpha and beta are. And then once we have that, we're going to say, okay, what is the probability of our data? And we're going to do this for each player, right? So we have the sum of our k's and our n's for kind of our different our theta values, and then we have our beta distribution, and so these are log things, so we're going to add them, d beta, theta, and alpha, and then we have finally the beta distribution for our proposed omega value. Okay, and so so that's what we have. And then for the Metropolis algorithm also, we need to have a proposal function. And so here I'm going to propose a random value of omega using the normal distribution. So I'm asking for, using our current value of omega, propose a new value of omega between using a standard deviation of 0.05, and omega has to be a value between 0 and 1. So if the proposed value is greater than 1, we'll use 1, and if the proposed value is less than 0, we'll use 0, okay? And that will return whatever our proposed omega value is here. All right, so all of this, I think I've scripted this. All right, so first I'm going to generate some imaginary players. So this is our imaginary batting averages. So we have 10 players, and some players' batting averages are lower and some are higher. So player 1's batting average is .252. Player 9 has a batting average of 321. Player 10 has a batting average of 282. Player 1, 2, 3 has a batting average of 246. Okay, and we're going to determine how many at-bats every player has. So the number of at-bats is not the same for everybody. Some have 500, some have more, some have less. Okay. And here I'm going to kind of do determine our hits and our outs. So I'm going to just create a big matrix, and basically I'm going to just generate some binomial values, and we're going to pad some zeros and ones here. Okay, so you can just kind of take a look. And just let's just see, how do I display Y? Let's look at like the first 20 rows for the first. Oops. Okay, we only have 10 players. Okay, sorry. Okay, so player 1, this is their sequence of hits and outs. Here, So if I just do like player 1, this is their sequence of hits and outs. And we can say, all right, how many hits did player 1 have? They had 118 hits, and okay, so if I do 521 minus 35, they had 486 at-bats. 118 divided by 486. This is their kind of current batting average, .242, which is a little bit lower than their, true, their theta value. All right, so they had 118 hits. They had a total of 486 at-bats. And so, our estimated, p hat for them is 0.242 or theta hat. But we have, 10 of these players, right? So that's player 1, and we can do the same for player 2 and so on and so forth. All right, so what we want to do is we want to figure out, okay, how many hits did every player have? So this is how many hits, and then how many at-bats did every player have, which is a little bit different. And so their empirical batting average is y over n, and let me just kind of round this off to 3. Okay, we're in here. 0.242. Oh, that didn't round off. Let me see. Okay, so this is kind of their our current kind of estimated batting averages versus what their imaginary batting averages are, as determined by so their empirical performance in 500 at-bats is higher, and some their actual performance is lower. But again, that's expected because of randomness, right? So their true batting average that we use to generate their values is 0.252, but then when they actually went up to bat, because of good luck or bad luck, this player performed a little bit lower. This player's true batting average that we used to generate was 0.275, but when they went to at bat, their actual performance was a little bit higher, a little bit lower, 0.282 in this case, and so on and so forth. Can we, using our data here, can we kind of figure out, a posterior distribution for what these things should be? So I'm going to do 15,000 iterations of our Gibbs and our Metropolis sampler here, and so here I'm going to create a huge matrix of theta values. Okay, so the dim for our thetas is I've got 15,000 rows and 10 columns. So we're going to generate for each. We have 10 columns, one for each player. And we're going to generate a random sample of 15,000 values for that player to kind of get a posterior distribution. And then we also need a bunch of what the omegas could be, right? Currently our omega is around 0.27, but maybe the true value should be a little bit higher or a little bit lower than that. We have hyper values, 3 and 7 for what the A omega and B omega are. K being a hyper value, 300 arbitrarily selected, and currently our value of omega is 0.27-ish, okay? Alpha and beta are determined using the formula relationship. And we're going to use the Metropolis algorithm. So we're going to propose random values of omega, given our current value of omega. And then to calculate our log probability here for any kind of proposed value of omega, we're going to calculate d binom of our k's and our n's. So again, k is the total number of hits, n is the total, total number of hits, n is the total number of at-bats. And so, we're going to take kind of our, a certain set of theta values, okay? I don't have theta values right now, but given a set of theta values, we're going to basically calculate d binom, and we're going to kind of sum them up. And then, so we'll include the sum of all of those things. Everything's working in log probabilities here. And then this is what we'll do. Okay, we will generate a random value for theta, and then we'll take that vector, the current most recently generated row of theta values, and using that we will propose a new omega value, and we'll calculate the probability, the log probability of the proposed values and the log probabilities of our current value of omega, to decide whether or not we will accept or reject that proposed value of omega proposed, using the log ratios, right? So we'll figure out the log probabilities of the proposed minus the log probability of our current. That's basically proposed divided by current, but in log. And then I'm going to generate a random uniform value, and if the log of the random uniform value is less than the difference in our proposed minus current, we will accept it, otherwise we'll reject it. Okay, so we'll go ahead and let this run, and I hope this works. Okay, it's done. All right, so we can look at what kind of values do we have for the omegas, okay? So this is a little bit hard to kind of see, but these are just a whole bunch of different random omega values. The histogram of the omega values ends up being centered at around 0.28, okay? If I add a density plot, it's kind of around there. So it's a little bit different from, when we did it ourselves, our omega value was closer to 0.27, but based on the data that we have, which is looking at k and n, let me do sum of k divided by sum of n, okay? Which aligns a little bit closer to what our data reflect. So with these 10 players, they're just because of kind of like randomness, their batting average ended up, overall batting average, if you take all 10 players into account, is closer to around 0.282, and therefore our posterior distribution kind of reflects that in our omegas. The mean of our omegas is around 0.281. Okay. We can look at what is the posterior distribution. Well, I've gone over my time for each kind of player, right, as well. So we can kind of say like, all right, what if we look at player one and what is their distribution? So player one, remember, player one had 118 hits out of 486 at bats. So their empirical batting average is 0.242. But when we generate a random sample, our estimate for their theta, taking into account their actual data, but also the prior distribution that's kind of shared among everybody, the median is around 0.258 for player one. Player two, who kind of outperformed a lot of other people, had 139 hits out of 493 at bats. Their empirical batting average is 0.281, and kind of taking into account their performance along with everybody else's performance, creating this shared beta distribution for everybody, their median batting average is around 0.282. And this is what we have here. Okay, I have gone over my time. Let me give you your last view quiz answer, which is the letter D. D as in dog. D as in dog. Okay, we'll continue this on next week, looking at JAGS. JAGS is stands for just another Gibbs sampler, but it's a way for us to kind of generate data and whatnot. Okay, but that's it for today. And again, no lecture on Wednesday, so have a happy Thanksgiving, and we will see you next week.